begin this unit of study with a discussion on how to write equations, balanced equations, for the so-called dissociation of ionic compounds in aqueous solution. So let's suppose we dissolve any of our ionic compounds. Of course, those are materials formed between metals and nonmetals, or metals with polyatomic anions, and they have distinct charge separation between the low electronegativity element and the high electronegativity element. And we talked at great length about the way we can connect these together by transfer of electrons and then the electrostatic attraction holding together the oppositely charged entities. So I'm going to take this ionic material and drop it into water, water being the solvent, and it inundates, as you can see the picture below. I'm showing a little model of little blue and orange spheres representing water molecules, and I have an ionic lattice of oppositely charged plus and minus ions connected together in a large segment. Now, what happens is that there's a homogeneous dispersal of small fragments of the ionic lattice among the water molecules. And we call this, of course, the process of dissolving. Now, this dissolving process is a physical change, meaning if I were to evaporate the water off of the sample, it might crystallize in a slightly different form, but the material will crystallize back into the exact same material that was present initially. So dissolving is not changing the composition of the matter, it is just changing the appearance of the matter, and it is therefore a physical change. We represent this chemically by saying the solid sodium chloride on the left as a reactant is becoming AQ, or aqueous sodium chloride, dispersed homogeneously among the water molecules. That's what this AQ means. And of course, as we're all experienced in noting, these once initially large chunk of sodium chloride disperses in small fragments among the water molecules and is no longer visible to the naked eye. And we call that dissolved salt in water. But that's not the end of the story. Water, it turns out, is a highly polar molecule. It has a distinct positive and negative end due to the large difference in electronegativity between the O and the H in the molecule, and actually also because of the really bent geometry due to the two sets of lone pairs on the oxygen. It's attempting to look tetrahedral, but two of the locations of the tetrahedron are occupied by non-bonding pairs of electrons on the O, so that the H's bond by sharing electrons at an angle less than 9.4 degrees, as 104.9 degrees, as we talked about for the tetrahedral arrangement around that central atom. So this bent over shape of the water molecule makes those bonds highly polar bonds because of the difference in electronegativity. So water, even though it doesn't have quite the charge separation that sodium and chlorine have in the ionic compound, it still itself is quite polar. The electronegative oxygen is the more negative end of the water molecule. Those accumulate around the cations in the ionic lattice. The positive ends of the water molecules are where the H's are centered, and as I'm depicting in my little picture here, that these water molecules with the H ends of them coalesce and gather more closely to the negative parts of the ionic lattice. So the entire crystal of water gets inundated, and remember, in a solvent-solute situation, there's way more solvent present than solute. So this crystal really gets inundated. Now it gets inundated to the point that what happens in actuality is that the individual charges begin to get yanked loose from the lattice. There are so many of these polar water molecules present, and their influence on the charged species in the ionic compound is so overwhelming that they literally begin to tear and shred the lattice apart. And the second equation represents the process by which we can mimic that occurrence in a symbolic representation of a chemical reaction. I say now the aqueous NaCl's are dissociated or ionized. I can use either of those two terms. I call this process ionization, or I call it dissociation. And what you see is I am pulling the ions apart into individual fragments. So not only does sodium chloride dissolve in water, sodium chloride dissociates in water. Now, a large number of its fellow ionic compounds experience this exact same behavior when placed in water. Not only do they dissolve, they dissociate, and they come into individual entities representing the plus and minus charge that each atom acquired in the formation of the ionic compound. Now, this might seem a little surprising to you, but this dissociation or ionization is also a physical change. It is not a chemical change. I've really not altered the Na or Cl from the way it existed in the ionic lattice. Remember, the highly electronegative chlorine stole an electron from the sodium, and in the solid lattice itself, I had sodium cations and chloride anions. Now that they've been inundated by the water and just shredded and ripped apart by the water, I still have sodium cations and chloride anions. However, there's just so many waters around, they aren't attracted to each other now, they are attracted to other water molecules. So they float free and independent of one another in the solution as individual charged species. Notice both sides of the ionization equation are balanced in terms of the number of NAs, in terms of the number of Cls, but also are balanced in terms of the total charge represented on both sides of the equation. There is zero net charge on the left NaCl side of the equation. When you sum the charge on the right, there is zero net charge on the right as well. Okay, so this is a physical change. I have not changed the material into a new form. As a matter of fact, if I were to evaporate the water away, guess what would happen? These opposite charged entities would stick back together, and I'd make a clump of sodium chloride on the bottom of the beaker. It might look recrystallized differently, but it would still be sodium chloride. So that's another indication that this is not a chemical change. It's just a different appearance of the same material that I started out with. Cartoons are attempting to represent what these ions would appear to look like if we could now nanoscopically observe what is going on in the dissolved and dissociated ionic compound present in water. Notice I have my sodium cations completely encapsulated by water molecules. Most importantly, the negative end of the water molecule orients itself so that it is pointing towards the positive cation of sodium. And on the other side of the slide, I show somewhere else floating in the solution a chloride anion as it might be depicted in this aqueous medium of water. There's an inundation of water molecules again, way more solvent particles than solute particles, so many so that they just essentially mob rush the anion as well as the cation, coating it completely with a sphere of these water molecules around each of them. But notice in the chloride case, the anion case, the positive ends of the water molecules orient themselves towards the anion. Now, of course, this is also, should technically be a three-dimensional representation, meaning I should have H's and O's orienting themselves into and out of the page. Around the sodium cation, I would have the oxygen ends of water molecules pointing to it, coming up out of the page towards me and behind the page away from me. And on the chloride anion, I would have the hydrogen end of water molecules sticking towards the chloride above the page and below the page. Now, typically what happens is there are so many water molecules around each other than there are chlorides or sodiums dissolved in the solution, that these hardly ever even encounter each other. As they move around through the solution, and they are mobile, and it's possible for them to float and move as the temperature of the solution is raised, they move more dramatically and rapidly. But this cage will move with them, or maybe if not all the water molecules want to go with it, others will take their place as this ion passes, and it associates itself around those particular anions and cations in this particular style. So this cage, if you like, either follows these around through the solution as it migrates around in the solution, or other water molecules just take the place of these particular ones as that ion moves around throughout that solution. And again, remember, in typical solutions, the solute is so minuscule compared to the solvent that essentially these sodiums or chlorides will never encounter each other very often, because there's just such an overwhelming amount of water compared to what is present for them individually. Now, of course, as you continue to put more and more salt in the water, the solute becomes more and more intensified in the water, and the likelihood of their encounter becomes greater and greater. And if they encounter each other, there is some likelihood that they could start to stick together. And if enough of them stick together, you create what we call a saturated solution, and these will begin to fall to the bottom of the solution. We've all seen what happens if you put too much salt in the water. There's simply not enough of these water molecules to form these hydration spheres to cage the salt and the cation and anions of the salt up efficiently, and so their own internal attractions take over and they fall to the bottom because their density is greater than the density of water, and gravity pulls them to the bottom because their mass to volume ratio is greater, and they sink and form a layer of salt in the bottom of the beaker if there are too many of them. Now, another thing we should recognize is that I've depicted this for sodium chloride, but I could equally well show the same thing for magnesium fluoride, for beryllium iodide, and even onto things polyatomic ions. I could show this picture for calcium nitrate. I could show a picture like this for sodium sulfate, and on it goes. The same sort of idea occurs where I have a so-called hydration sphere surrounding the cations and anions that I have dissolved in this massive amount of water. But one thing you should definitely recognize is the fact that the bulkier and bulkier the anion or cation get, the larger the hydration sphere, or the more water molecules it would take to encapsulate it. This is particularly true for polyatomic anions. Think about what you would have to, how many water molecules you'd have to use to cage up, say, a phosphate anion, PO4 minus 3. Think of how much more bulky that is in the solution compared to the chloride anion. It would take way more water molecules to encapsulate it. So what that ultimately ends up meaning is that the solubility of a compound like sodium phosphate is less than the solubility of, say, sodium chloride. Because it would take so many more waters to be involved in the hydration sphere, there's literally going to be less phosphates you can get into solution compared to how many chlorides you can get into solution. So there's a varying degrees of solubility of various ionic compounds based on not several other factors as well, but one of them, of course, would involve how big and bulky these particular species are that you're trying to dissolve in water. There, believe me, are several other factors involved as well, but that's certainly among them. Ionic compounds dissolved in water have a familiar name to us all, and that name is that they are called electrolytes. And the reason they are called electrolytes is that when they dissolve, they not only dissolve, they dissociate. And when they dissociate, they form these broken apart fragments in the water that are charged. And now I could influence them to move due to the polarity of electric field. So they can create a current in the solution. So when you have these ionic species dissolved in water, they can create a flow of charge and conduct electricity very, very well. As a matter of fact, this might be surprising to you, but water itself is a very good insulator toward that electricity. Water is not a good conductor of electricity. As a matter of fact, any material which is molecular is often not a good conductor of electricity. It turns out this is because the polar covalent bond is much stronger than the ionic bond in terms of the sharing of electrons between the two atoms. So this makes it more difficult for the atoms to be ripped apart and make charges in water. So things that use covalent or polar covalent bonds are typically what we call non-electrolytes. So molecules or things using polar covalent bonds are non-electrolytes, and they stick together in solution, and things which are ionic compounds placed in water are called electrolytes. They break apart into charges in water, and you'll note here I'm showing the form of both kinds of equation. On the bottom I have the dissociation of not dissociation, I just have the dissolving of a non-electrolyte, and that would happen to be sucrose in the case that I'm showing at the bottom of the slide. Above, I'm showing the dissociation and actual break apart of ionic compounds which form charges. So these are electrolytes when placed in solution. Now, of course, one of the things I'm going to be requiring is that you can write these balanced equations for the dissociation of these compounds in water. So you should recognize from the way KBr bonds, because K is in column 1 and Br is in column 17, that they are, of course, +1 charge for the potassium and -1 charge for the bromine. So when they come apart, they are forming K +1s and Br -1s in solution. Compare that to, say, if I was dissolving MgO. Even though that's a 1-to-1 species, you should be able to recognize that because Mg is in column 2 and O is in column 16, Mg prefers to be a +2, O prefers to be a -2. So if I were to write the dissociation of MgO, it would be Mg +2, O -2. You have to be able to write balanced equations that show the correct dissociative forms with the correct charge on the species that are dissolved among the water molecules. Now, this is also true with our friends, the polyatomic anions. You should know by now that nitrates are always -1, and when I have the compound MgNO3 taken twice, when it dissociates in water, magnesium being a column 2 element is going to be a +2 cation, and I will have 2 nitrates, each being -1. Notice how I wrote the balanced equation for that by representing the NO3, not by dissociating it. Now, again, remember, NO3 itself is polar covalent. Internally, the polar covalent bonds that hold that together are too strong for water molecules' polarity to pull that apart. So I don't experience a dissociation of the nitrate because of the polarity of it in the solution. I'm sorry, because of the polarity of the solution. The water molecules are not highly enough plus and minus charged to yank apart the polar covalent bond of the nitrate. So it remains intact molecularly in the solution, as you see in the representation I'm showing. Recap what we've been discussing, comparing the bond types to their behavior when placed in aqueous medium. If you have ionic bonds, they're the weakest type of bonds, and they're so weak that the polarity of an inundating sample of water can just shred them apart and form hydration spheres, encaging the individual cations and anions. So ionic compounds, or any compounds that are formed from metals and nonmetals, we're going to assume, are going to be able to be dissociative or fall apart into charged species when placed in aqueous medium. Covalent or polar covalent species, which we earlier called molecules, and molecules have this individual entity that we talked about, how they don't concatenate together to compound. So I show the polar covalent molecule water, ammonia, a liquid sample of ammonia that I place in water will just dissolve among the water molecules, hide and disperse among them homogeneously, spread evenly among the water molecules, but it will not rip the ammonia molecule into fragments of positive and negative charge. And ammonia is a non-electrolyte when placed in solution. And lastly, another thing to keep in mind, if I put an ionic compound into solution which contains a polyatomic anion or even a polyatomic cation for that matter, the polyatomic ions are held together with polar covalent bonding, and the water is strong enough to pull apart the ionic attraction between the polar covalent ionic polyatomic ion and the thing it's connected to, but it is not strong enough to pull apart the cation. It can pull the cation loose, as we see here, but it can't pull and break the polar covalent bonds in the phosphite that I'm showing at the bottom. So the phosphite remains intact molecularly. Notice that bottom equation shows a balance of the number of BEs and PO3s on both sides, and it shows a balance of the charge on both sides. There's 6 units of negative charge on the right and 6 units of positive charge. Added together, there's 0 net charge on the right, matching the 0 net charge on the left. Slide I show some other examples. Again, remember, I'm going to expect that you are able to write balanced equations for dissociation. This means that you're going to have knowledge of the charge that these particular materials like to take when placed in solution. Like, for instance, on the bottom one, how would you know what the charge of the chromium is? Because it is, as you remember, one of these transition metals where you have to indicate what the charge is. Well, what I'm saying is you should be able to tell what charge the chromium is based on the number of chromiums that have to combine with sulfite. Sulfite is always -2, as we see when I dissociated it there. And again, really, to make the least common multiple of electrons transferred in the chromium sulfite, it had to be chromium 3 sulfite, because I'm giving up 6 electrons from the sulfite. I'm sorry, not the sulfite, that's a sulfate, excuse me. And I'm giving 6 electrons from the chromium. 2 Cr plus 3s, 3 SO4 minus 2s, and that has a balance of charge being transferred between the two. I'm sorry, above that, I meant to say phosphite is in the lithium phosphite above that. Lithium is a column 1 element, is always going to be a +1. Phosphites are always -3. Notice I don't, when I dissociate this, just like we talk about when we balanced chemical equations before, I don't write Li subscript 3 for the balanced equation. The 3 goes in front, saying every time one lithium fight falls apart, 3 lithiums come out of it. So make sure you don't put subscripts when you dissociate these. You put coefficients in front representing the number of particles that are coming apart as the ionic compound dissociates. This slide shows some examples of the ionizations of acids or bases. This is one of the hallmarks of the behavior of acid and bases in solution. Again, I'm writing these as physical changes, but it turns out, as you will learn next semester, acids and bases are a little bit different. They actually often hydrolyze with water, or hydrolyze means reacts with water, but that's really not a topic that we're taking up in this particular section that we're doing here. All I would prefer that you are able to do is write the equations showing balanced loss and gain of materials in terms of the charge being broken apart as the ionic species dissociates, and also the number of atoms coming apart as the material dissociates. So you should be able to write a balanced equation for the dissociation of hydrochloric acid, as I showed first, then nitric acid, or a base, which is a material which contains a hydroxide anion. Notice the calcium hydroxide dissociating at the bottom makes calcium +2 and 2 hydroxide anions as a result of that dissociation. Now introduce the concept of the limiting reagent. Typically when we do a reaction, we don't put the proper proportion of the reactants in the pot. We scoop some reactant A, we scoop in some reactant B, and they begin to form C and D, the products. Well, unless they are put in the exact stoichiometric ratio, then they don't disappear 1 to 1 to 1 to 1 to 1, and then when the reaction is over, every bit of each is consumed. When they're not mixed in the proper proportion, one of them is consumed first. And the reactant which runs out before other reactants run out is known as the limiting reactant, or more commonly the limiting reagent. Once the limiting reagent is gone and there's no more of that reactant around, the reaction cannot proceed any further. So the amount of product being formed is dictated by the limiting reagent. So what we're going to do on the next several slides is look at the consequences of mixing reactants in an improper proportion so that one of them runs out first before the other and the reaction stops. Let's look at the example of the reaction of calcium and sulfur to form calcium sulfide. We see the stoichiometry here is 1 to 1 for the reactants and 1 to 1 for the products. Suppose you put 5 atoms of calcium in the pot, 10 atoms of sulfur. They react 1 to 1 to 1 to 1 to 1 to 1 until 5 calciums are consumed, and then the reaction must cease when the calcium is all gone. And when I open the pot, based on the stoichiometry, I used up 5 calciums. That means 5 calcium sulfides must have been formed. Now notice also, though, that this product is contaminated because there are 5 excess sulfurs that do not go into the calcium sulfide. And when I open the pot, there are 0 calciums, 5 calcium sulfides, and of course 5 sulfur atoms remaining. In the case that I mix 135 atoms of calcium with 22 atoms of sulfur, again, because the stoichiometry is 1 to 1, they react till 22 of the sulfurs have disappeared. There are no more sulfurs for the calciums to react with, so the reaction ceases. Sulfur is the limiting reagent. As a matter of fact, when I open the pot, there would be 22 calcium sulfide units in the pot, and there would be 113 calciums in the pot contaminating those 22 calcium sulfides. Nature maintains that all the atoms are accounted for according to the ideas of Dalton as well. Now, more realistically, I'm not going to do this in individual atoms. I can't perceive those. I would do those more in the quantity that is the bushel basket of chemistry, which of course is the mole. So if I were to react 1.75 moles of calcium with 3.25 moles of sulfur, 1 mole goes away, 1.5 mole go away. After 1.75 moles of the calcium are consumed, there's no more calcium to react, so the reaction ceases. And we can also do a little bit of quick figure in here. There would be 1.5 moles of sulfur in excess because only 1.75 moles are used up based on the amount of limiting reagent and the stoichiometry. There's a 1-to-1 stoichiometry, so after 1.75 moles of the calcium are gone, 1.75 moles of the sulfur is gone. And since I put 3.25 moles in there, there's still 1.5 moles of sulfur remaining. I also would note that there would be 1.75 moles of calcium sulfide formed because of the connection with the stoichiometry. Now, another thing to keep in mind, remember, in this particular case, moles are a real number. So this is a measurement of the number of moles of calcium and sulfur to 3 significant figures. Now, to be honest, to get it to the proper significance as to count every atom in the pot would be virtually impossible. Remember, Avogadro's number, which converts atoms into moles, is 6.02 times 10 to the 23rd atoms per mole in or up to 3 significant figures and not beyond that. Now, if in the chance that you put 20.5 moles of each reactant in, they disappear consecutively and to the exact same extent, and when those 20.5 moles of calcium are consumed, simultaneously 20.5 moles of sulfur are consumed. Now again, remember, this is accurate to 3 digits of accuracy. To really think that you're matching the calcium to the sulfur perfectly when you're counting it in moles is really a virtual impossibility. But for up at least out to 3 significant figures, we have mixed the calcium and sulfur to the exact so-called stoichiometric ratio or stoichiometric mixture. Now, of course, when those 20.5 moles of these 2 reactants are consumed, because of the stoichiometry with the products, 20.5 moles of the calcium sulfide would have been formed when those reactants are consumed. Realistically, if we're going to do this process in a laboratory, we would not use mole tweezers to get the reactants out and put them into the pot. We would weigh them on the scale. So let's suppose we go to the scale and we weigh 25 grams of each of the calcium and the sulfur. Now, again, remember, it looks maybe at first glance like this is a stoichiometric ratio again, but the balanced equation does not tell you anything about the mass of reactant A to reactant B. It tells you about the number of reactant A to reactant B. The number of calciums, according to the balanced equation, should match the number of sulfurs. So from the mass of the calcium and the mass of the sulfur, we must first determine how many calciums, how many sulfurs are present. So we should take the molar mass of calcium from the table, divide that into the mass of calcium, and find that there's 0.624 moles of calcium. Take the molar mass of the sulfur, divide that into the mass that I put into the pot, and I would see that there's 0.780 moles of sulfur. So by comparing those, and since they react 1 to 1, I have less moles of calcium than sulfur, so that the calcium is the limiting reagent. And as a matter of fact, I know for sure that I would be forming 0.624 moles of calcium sulfide because the limiting reagent is in a 1-to-1 stoichiometric ratio to the product. And I would also know that there's an excess or a remainder of 0.056 moles of sulfur in the pot. Why? Because 0.624 moles are consumed. If I subtract 0.624 moles from, oh no, I said that wrong, I guess. It's 0.1, let's back that up again. When I do that subtraction there, I'm going to get 0.156, yes, sorry. I did that in my head. My subtraction was not too good. So when I subtract 0.780 moles of sulfur from 0.624 moles of calcium, because they combine 1 to 1, there'll be 0.156 moles of sulfur excess in the pot, in addition to the 0.624 moles of calcium sulfide that are formed in this reaction. Also be able to compute the mass of that excess reactant. Let's look at this example problem where I'm reacting boron and phosphorus to form boron phosphide. Again, notice this is a balanced equation. And suppose I put 10 grams of boron mixed with 20 grams of phosphorus, and I want to know which is the limiting reagent and how many grams of the excess might be left in the pot. What I will do, of course, is note, it looks like I have an excess of phosphorus based on the masses, but you can't confirm that until you count how many phosphoruses are present in 20 grams and how many borons are present in 10 grams. So what I need to do is find the molar mass of boron, which is 10.81 gram per mole, divide that into the mass of boron, and I find out I have about a mole of boron. Then when I divide the 20 grams of phosphorus by its molar mass, I find I only have 0.646 moles of phosphorus. So since the boron and phosphorus are combining in a 1-to-1 ratio, since I have less moles of phosphorus than I have boron, I know, and I can conclude that the first part of this problem is that phosphorus is my limiting reagent. On to determining how much excess B is in the pot. We've now determined that phosphorus was the limiting reagent. So how much B is in excess? From the previous slide, I had found that I had put in my 10 grams of boron, 0.925 moles of boron. I found when I put my 20 grams of phosphorus, I had put 0.646 moles of phosphorus. They begin to react 1 to 1 to 1 to 1 until all moles of the limiting reagent are consumed, which of course represents 0.646 moles of the limiting reagent. And so I can subtract that from the excess reactant and find there's 0.279 moles of boron remaining in the pot. Now I wish to know what mass of boron is excess in the pot. I would take my 0.279 moles times the molar mass of boron, and I would find that 3.02 grams of boron were wasted because there was not enough phosphorus to react with them. Okay, so where's the rest of the boron? Of course, where I could find it is in the boron phosphide compound. As a matter of fact, I began with 10 grams of boron. There's 3.02 grams of it left. That means that 6.98 grams of the boron are in the BP. Now I could also do that similar calculation by noting that, of course, there's 0.646 moles of BP being formed, and I can use the molar mass of BP and find how many grams of BP are formed. I can do it right here as well because, of course, all 20 grams of the phosphorus are gone because phosphorus is the limiting reagent. There's no moles of it left. There's no mass of it left. 20 grams of it have disappeared. They didn't disappear into thin air. They went into the boron phosphide. And as we just discussed, we began with 10 grams of boron. 6.98 of the boron are gone. So 6.98 grams plus 20 grams means that the mass that has disappeared from the reactants is all in the products. There must be 26.98 grams of BP in the pot. And I bet if I took 0.646 moles of BP times the molar mass of BP, I would find that number would be 26 0.98 grams because nature works in this very systematic way. Verify that previous assertion by doing another example. Here I'm going to form calcium selenide by reacting elemental calcium and elemental selenium. I have mixed 15 grams of calcium with 15 grams of selenium. It looks like a stoichiometric ratio, but I have to check with how many moles of each I put into the pot. So let's first determine which is the limiting reagent, figure out how much of the excess reactant is remaining in the pot with the product, and actually how many grams of the product there actually are formed. So first I'm going to take my 15 grams of each reactant. I'm going to look up the molar mass of calcium, the molar mass of selenium. I'm going to divide 15 grams by each of those values and find that if that is the case, then there is 0.374 moles of calcium and 0.190 moles of selenium in the pot. Because the calcium and selenium react 1 to 1, I put less moles of selenium than calcium, so selenium is therefore the limiting reagent. Now find the mass of excess reactant. I find from the previous slide that the 15 grams of calcium correspond to 0.374 moles. The 15 grams of selenium correspond to 0.190 moles. They disappear and disappear 1 to 1 to 1 to 1 to 1 until the limiting reagent is consumed. So when that occurs, the 0.190 moles of selenium are gone. And since the stoichiometry is 1 to 1 with the calcium, 0.190 moles of calcium are consumed at the same time. So if I subtract 0.190 from 0.374, I find that there's 0.184 mole of calcium in excess. And then if I turn to the molar mass of calcium, multiply it by those excess numbers of moles, I would find 7.37 grams of calcium left in the pot. Now remember, I began with 15 grams of calcium. That means 7.63 grams of calcium have disappeared. Where did those 7.63 grams of calcium go? Did they go into thin air? Were they swept under the rug of the universe? No. The 7.63 grams of calcium which have disappeared are in the calcium selenide. On the previous slide, we found that 7.37 grams of calcium are gone. That meant that 7.63 grams of calcium are in the product compound. And of course, the limiting reagent is entirely consumed, and there was 15 grams of it to start. So there are 15 grams of selenium in the product compound. There's 7.63 grams of calcium in the product compound. So that makes a total of 22.63 grams of calcium selenide if I add the total of the limiting reagent to the missing amount of the excess reagent. But we could also determine this directly from the stoichiometry of the limiting reagent to the product. There was 0.190 mole of the limiting reagent to begin with, and because the stoichiometry of the limiting reagent to the product is 1 to 1, that means that 0.190 mole of the product molecule must be formed. If I now calculate the molar mass of calcium selenide by adding up the molar masses of calcium and selenium, I find that's 0.04 grams per mole. So I multiply the moles of product formed by that molar mass, and I find, as I just stated, voila, 22.6 grams of calcium selenide must be formed. So the bottom statement is just saying that there must be a mass balance between the limiting reagent disappearing and the excess reactant that is disappeared, and the total of the product that is being formed. let's define a couple terms relevant to the experiment that we perform in laboratories when we synthesize compounds. Those would be the so-called theoretical and percent yields. The theoretical yield is the amount of product that you should actually form if the reaction works perfectly. So the theoretical yield is the calculated yield. It's what you determine on paper that you should make when you mixed a certain component, a ratio of reacting components. Now, of course, in the real world, just because you mix these components doesn't mean that the amount of product you formed will be exactly based on the stoichiometric ratio of the reactants you put in there. All kinds of things can go wrong, including the chance that the reaction comes to equilibrium, which means it doesn't go to completion. It goes to a certain extent, and then the reverse reaction starts to decompose the product back into the original reactants. So very commonly, reactions do not have a complete extent. They come to a certain buildup, a product formed, and then from that point on, no more product is formed because it is decomposing as it is forming at the same rate that it is forming. So what we often then calculate is a so-called percent yield. Percent yield measures the fraction of product that is actually being formed compared to what the maximum amount of product you think should be formed. So the percent yield is a fraction typically less than 1. It could be exactly 1 if the theoretical yield and experimental yield match. But typically, the experimental yield divided by the theoretical yield is a number less than 1, and then you multiply that fraction by 100 to change it into a percent. Now notice, the units of the experimental yield and theoretical yield should be the same. They can be measured in grams, pounds, kilograms, but they must be measured in the same mass unit in order for those mass units to cancel. There's technically no real units in a percent yield other than a percent sign. Now, and technically, you could measure the experimental yield and theoretical yield in moles. As long as they're both measured in moles, the mole units cancel, and you would get the same percent yield if you measured and used masses in grams, or if you used amounts in moles. It would work out the same as it should in either case. So the bottom expression is simply saying kind of what you're doing experimentally. The percent yield is what you actually get in some particular unit that you measure, divided by what you should have got, what you calculated you should have got on paper, as long as those are measured in the same unit. That should be a fraction less than 1. You multiply that fraction by 100 to change that fraction into a percentage. Some examples using the percent yield expression. Suppose a reaction has a theoretical yield of 12.7 grams, and the experiment actually produces 3.38 grams of product. What was the percent yield? I can just divide what I actually got into what I should have got, or by what I should have got, multiply by 100. Notice the mass units cancel. But when I multiply by 100, it really gives me a unit of percent, if you like. So this would have been a 26.6% yield. Now these are numbers of significance as well for those of you that are fans of significance. I have 3 significant figures in my theoretical yield, 3 significant figures in my experimental yield. I have 3 significant figures in my percent yield as well. So if I have a percent yield of 58.1% and a theoretical yield of 0.885 grams, I can find the experimental yield by taking that percent yield and multiplying it by 100, or I'm sorry, multiplying it by 100, dividing it by 100 to change it into a decimal. So essentially I divided both sides of the expression by 100, and I have 0.581, the decimal equivalent of the fraction of the experimental yield divided by the theoretical yield. So I can multiply both sides by the theoretical yield, and again to 3 digits of accuracy. That means my experimental yield that gives that percent yield must have been 0.514 grams. So a sample problem where we calculate the theoretical yield and percent yield from a limiting reagent problem. Here I'm reacting calcium with molecular hydrogen to form calcium hydride. Notice this is a 1-to-1-to-1 stoichiometry, a balanced equation. So I'm going to use 3 grams of H2 mixed with 35 grams of Ca, and I find that when I do this experiment, I make 30.8 grams of calcium hydride. So from the mass of reactants that I put in the pot, I'm first asked to find the limiting reagent. Once I find that limiting reagent, I'm asked to find how many grams of excess reactant remains. It looks like calcium is way in excess to hydrogen, but we better check before we come to that conclusion. And since I know that the experiment actually produced 30.8 grams of the calcium hydride, I'm asked to find the percent yield, and in order to do that percent yield, I'm going to need to find the theoretical yield of calcium hydride. So we'll do that on some subsequent slides. We first take our 3 grams of hydrogen, use the molar mass of H2, notice, and I find I had about 1.5 moles of hydrogen, my 35 grams of calcium, divide by its molar mass. I find that I have 0.873 moles of the calcium. And of course, from those numbers, because the stoichiometry is 1-to-1, the calcium is the limiting reagent. Now, if I find the excess hydrogen that I wasted in the pot, I will subtract the moles of the limiting reagent from the moles of the molecular hydrogen, since they are reacting 1-to-1, and I have 0.62 moles of hydrogen remaining. And when I transform that with its molar mass, I find that I have 1.2 grams of molecular hydrogen remaining. Now remember, I began with 3 grams of molecular hydrogen. That means 1.8 grams of it have disappeared. And of course, where they disappeared into is into the product of the calcium hydride. Of course, all of the limiting reagent is gone. 35 grams of it are gone, plus the 1.8 grams of hydrogen that is gone. So that means that my theoretical yield of calcium hydride had better be 35 plus 1.8, or 36.8 grams of product being formed. But on the next slide, what we'll do is we'll make sure that that is the case by checking it via the stoichiometry of the limiting reagent to the product being formed. We will find the mass of calcium hydride being formed based on the stoichiometry of the limiting reagent. The limiting reagent was 0.873 moles of calcium. Because the stoichiometry of the calcium to the calcium hydride is 1-to-1, I can convert the 0.873 moles of reactant into exactly 1-to-1, using that as a conversion factor, into 0.873 moles of calcium hydride product. Calculate the molar mass of calcium hydride by adding up a Ca and 2 H's, find it to be 42.1 gram per mole, multiply that times the moles of product formed, and voila, just like we said on the previous slide, 36.7 grams of calcium hydride are being formed. So that matches closely to what we just talked about on the previous slide. Find the percent yield of the calcium hydride. According to the word statement of the problem, there was 30.8 grams of calcium hydride actually formed in the process. On the previous slide, we found a theoretical yield of 36.7 grams of calcium hydride. So I can find the percent yield by dividing the theoretical yield into the experimental yield, multiplying by 100, and I get an 83.9% yield for this particular experiment. I've noticed one simplifying factor in all the examples we have worked so far. That was a 1-to-1 1 stoichiometry. Let's look now at some examples of what we have to deal with when there is some ratio and proportion of combination. Like for instance, in this formation of iron oxide from elemental iron and molecular oxygen. Notice to balance this equation, I need 3 Fe's plus 2 O2s to make 1 Fe3O4. And let's suppose I put 1 mole of the iron and 1 mole of the oxygen into the pot. What I need to do is it looks in the previous example that would have been a stoichiometric ratio if the moles of Fe reacted 1 to 1 with the moles of O2. But here there's a 3 mole Fe to 2 mole O2 reaction. So what we can do is we can do this in one of 3 ways actually. I can take my moles of Fe and see how many moles of O2 that will require to react completely with it. I can take my moles of O2 and see how many moles of Fe it will take to react completely with it. Or I can take the moles of each of these reactants and see how many moles of the product they will form. So let's just do each of these various ways and argue as to how they show which is the limiting reagent. They should all show the same thing, by the way. So I'm going to begin by taking my moles of O2 and calculating if every bit of that O2 disappears, how much Fe will be required to react with it. Based on the stoichiometry, I make a conversion factor that 3 moles of Fe react when 2 moles of O2 react. Again, those coefficients, as we did in our last unit of study, come from the balanced stoichiometry of the problem. Now, notice that stoichiometrically, the dimensional analysis says that the moles of O2 cancel. My answer is now in moles of Fe. So dimensionally speaking, I've eliminated the O2 and converted it to Fe. So now I know I can multiply the numbers and divide the numbers because they're lined up correctly. So I'll take 1 times 3 divided by 2. And what it's saying is if I use the entirety of 1 mole of O2, I will need 1.5 moles of Fe. I look at how much Fe I put in the pot. I only put 1 mole in, but if all the O2 is used, I will need 1.5 mole of Fe in there with the O2. So there's not enough Fe, so Fe is my limiting reagent. Now let's draw the same conclusion. I'm going to do the same problem, but now from the perspective of the Fe. If I use all of the Fe and stoichiometrically convert that into how much O2 it will consume if it is all used up, I need a 2 to 3 ratio because notice I'm canceling the Fe in the second part of the example. So the Fe part of the stoichiometry goes on the bottom. That puts the O2 part of the stoichiometry on the top. And the moles of Fe cancel and will tell me that how many moles of O2 react with those moles of Fe. So this tells me take 1 times 2 divided by 3. And what the statement is saying is that if all 1 mole of the Fe is used, only 0.667 moles of the O2 will be used at that same time. There is more O2 in the pot than that, so that the Fe will run out before all the O2 runs out, so that Fe is still the limiting reagent if I had done so by comparison of the O to Fe or by comparison of the Fe to the O. Slide I am working the exact same problem, but now to determine the limiting reagent, I'm going to compare how much each of these reactants, how many moles of product each will form. The one that will form the least amount of product will be the limiting reagent because that is the limit to how much product that can be formed if all of each of these reactants is consumed. Now notice for the Fe, there's a 3 to 1 ratio between the Fe and the Fe3O4 in the balanced equation. So I line up the stoichiometric coefficients to cancel the Fe and leave me in moles of Fe3O4. So when lined up correctly, I need to take 1 times 1 divided by 3, and what it's saying is that if I use the entirety of 1 mole of Fe, I will form 1/3 of a mole of Fe3O4. Now let's see how much Fe3O4 can be formed if if I use all of the O2. The stoichiometry between O2 and Fe3O4 is 1:2 ratio. So I line that up as a stoichiometric conversion factor to eliminate the moles of O2 and convert using all those moles of O2 into product Fe3O4. Now I will use the 1:2 ratio to compare the O2 to the Fe3O4. And when lined up correctly, this means I take 1 times 1 divide 2. If I use all the O2 according to the stoichiometry, I will form 0.5 moles of Fe3O4. Since more moles of Fe3O4 would be consumed or formed when using up the O2 as compared to using up all the Fe, I know that Fe must be the limiting reagent. So Fe was determined to be the limiting reagent by comparing how much O2 will be formed by using all the Fe, or by seeing how much Fe is needed if all the O2 is used, or by forming the product from each of the starting materials and finding which is the minimum amount of product that each starting material can form. It turns out that this is typically what I note most students do it this third way than any other way. They take the amount of starting product, or reactant, calculate based on stoichiometry how much product will be formed from each reactant, and the reactant which forms the least amount of product is the limiting reagent. Again, this is typically the way I see most people working this problem. Look at another example, this time the synthesis of ammonia from molecular H2 and N2. Suppose we begin with 8.25 grams of H2 and 52.5 grams of N2. We want to find out which is the limiting reagent from this mixture that we put in the pot. The first thing I'm going to do is find out how many moles of H2 are present and how many moles of N2 are present. So I will divide by the molar mass of each. I find there are 4.09 moles of H2 and 1.87 mole of N2. Now to determine which is the limiting reagent, what I will do is see which will form the least number of moles of product. And I note that the stoichiometry between the H2 and the product NH3 is 2 to 3. So I begin with my moles of H2, line up the stoichiometry to the product NH3 as you see, and I see that if I use all the H2, I will form 2.73 moles of NH3. And if I began with 1.87 moles of H2, but now I see and check how much NH3 is formed if I use, I'm sorry, I said H2, I meant N2. I see how much NH3 is formed if I used all the N2. There's a 2 to 1 stoichiometry between the NH3 and the N2. So using up every bit of the N2 would form 3.74 moles of ammonia. Since more moles of ammonia are formed from the reaction of all the nitrogen compared to the number of moles formed by reaction of all the H2, I verify that H2 is the limiting reagent in this case. Let's look at the example of forming water by reacting molecular hydrogen and oxygen. We mix 5 grams of molecular hydrogen with 5 grams of oxygen. Let's first determine which is the limiting reagent. Then let's figure out how much of the excess reactant was placed in the pot. First, I'm going to find the molar mass of H2 and O2, convert the 5 grams of each into moles of H2 and moles of O2. Then what I will do is use the stoichiometry between each reactant to the product and determine which of them, or how much product each of them will form if the entirety of their sample is used. When I look at the 2 to 1 ratio of water to H2, I find that if I use all, I'm sorry, it's a 2 to 2 ratio, sorry. of H2O to H2 in the balanced equation. So if I start with 2.48 moles of H2, and if I use it all, I would make 2.48 moles of H2O. I started with 0.156 moles of O2 based on the molar mass of it and how many grams I began with. The stoichiometry of H2O to O2 is 2 to 1. So converting the moles of O2 into the total number of moles of H2O it could possibly form, I find that it could possibly form 0.312 moles of H2O. Since the O2 that is present will form the least amount of product, it must be the limiting reagent, because when that least amount of product is formed, the limiting reagent is gone and no more product can be formed. So we find that O2 is the limiting reagent. Now that I have determined that O2 is the limiting reagent, in order to find out how much excess H2 was in the pot with that O2, what I will do is I will use the moles of O2 that I have, see how much possible H2 it can use up. So what I do is I began with my 0.156 moles from the previous slide. Because there's a 2 to 1 ratio of H2 to O2, I find that using every bit of that 0.156 moles of O2, we'll use 0.313 moles of H2. I had 2.48 moles of H2 total in the pot. The O2 can use up 0.313 moles of it, so I subtract that from the starting number of moles of H2 and find 2.17 moles of H2 remain. Now all I have to do is convert the moles of remaining H2 back into the mass of remaining H2, and when I multiply the remaining moles by the mass, I find 4.37 grams of H2 remain. Now remember, I only started with 5 grams of the H2 and 4.37 grams of the H2 remain. That means 0.63 grams of H2 are gone. And of course, where did that 0.63 grams of H2 go? It went into the product. Of course, the entirety of the limiting reagent is in the product. That was 5 grams of O2. There's 0.63 grams of H2 gone. So that would mean that a mass of 5.63 grams of H2O must have been formed. We can explore that on some upcoming problems and examples that we will do. Explore the stoichiometric problem where we have a limiting reagent and we want to find what the percent yield is if we have a given experimental yield. In this case, I'm going to mix 0.5 gram of H2 with 15 grams of N2, and I'm going to produce ammonia. So I want to first figure out which is the limiting reagent. I want to figure out how much of the excess reactant I'm wasting, and then I'll figure out the percent yield by determining the theoretical yield of ammonia that the limiting reagent allows me to produce. So first I'm going to take my mass of the two reactants, find their molar masses, and convert the mass into moles so I can use the balanced equation to compare from the stoichiometry, which is the limiting reagent. So I find 0.248 moles of H2, 0.535 moles of N2. Now to determine which is the limiting reagent, I'm going to find stoichiometrically how much each reactant, how much product each reactant can form if that total reactant is completely consumed during the formation of product. There is a 2 to 3 ratio between the H2 and the NH3. So when I convert the moles of H2 into moles of NH3, I find that using all 0.248 moles of it will form 0.165 moles of ammonia. There is a 2 to 1 stoichiometry between the ammonia and the N2. So if I use all 0.535 moles of my starting N2, I would, according to the stoichiometric conversion, form 1.07 moles of ammonia. since I'm forming more moles of ammonia from the N2 than I can possibly form from the H2, the NH3 production will cease when the H2 production of it ceases. So H2 must be my limiting reagent because it can form the least amount of product. Let's now find how much excess N2 must be in the pot. So what I will do is take my limiting reagent, use the stoichiometric ratio between it and the excess reactant, and I will find when I use all the limiting reagent, I will use 0.083 moles of the excess reagent. And what I know is I began when I put 15 grams of the N2 in the pot, that I had begun with 0.535 moles of N2 in the pot. So I take my starting number of moles of N2, subtract the number of moles that the limiting reagent can consume, and I will have 0.452 moles of the N2 remaining after all the H2 is consumed. I take my 0.542 moles of N2, convert it back into the mass of N2 that is equivalent to, and I find that is 12.7 grams of N2. Now remember, I put 15 grams in to begin with, so that means 2.3 grams of N2 are gone from the 15 grams I started with. And where did that 2.3 grams go? That 2.3 grams must have went into the product. The entirety of the limiting reagent is in the product. That was 0.5 grams of H2, plus the excess reactant has placed 2.3 grams of N2 into the product. So that means 2.3 plus 0.5, I must be making 2.8 grams of the NH3 as a result. But let's check that by using the stoichiometry on the next slide. Verifying the mass of NH3 being formed, I begin with the limiting reagent, as I did on the first slide, as a matter of fact, and I have 0.248 moles of it. I use the stoichiometric ratio of the NH3 being produced to the moles of H2 being consumed. That is a 2:3 ratio, and as I found on a previous slide, using all of the H2 will produce 0.165 moles of NH3. Now I find the molar mass of NH3, which is found by, of course, adding an N with 3 H's to be 17.03 grams. I multiply that times the number of moles of product being formed, and lo and behold, as I predicted on the previous slide, I'm going to form 2.8 grams of my ammonia. So my mass balance checks out with the masses of the reactants I use and how much excess reactant remains when all the limiting reagent is consumed. The final step is to use this theoretical yield to find the percent yield. The word statement of the problem said that the experiment produced 2.55 grams of ammonia. I have now determined that on paper, if everything goes perfectly, the entirety of the limiting reagent could possibly form 2.81 grams of ammonia. So I will divide the 2.81 into the 2.55, get a fraction of 0.907, but I multiply that times 100 to get a percent yield of this particular experiment to be 90.7%. Remaining time, let's do one more of these limiting reagent problems with stoichiometry, where we find all the components like you can expect I'm going to ask you to do on our final assessment. Suppose I take 2 phosphorus atoms and combine them with 3 molecules of hydrogen to form 2 pH3 molecules, and I begin with a gram of H2 mixed with 12.5 grams of phosphorus. Let's ask questions that you would similarly see on the test. What's the limiting reagent? How many grams of the excess remain? And I give you an experimental yield, and you tell me what the theoretical yield or I'm sorry, what the percent yield would be. So that means you have to find the theoretical yield you have to find the theoretical yield to find the percent yield. First, let's find which is the limiting reagent by comparing which will form the least amount of product. So my 12.5 grams of P, I divide by its molar mass, and note that I had 0.404 moles of P. My 1 gram of H2 dividing by its molar mass means I had about a half a mole of H2. Now to verify which of these is the limiting reagent, I will stoichiometrically compare how much product each can possibly form. The ratio of H2 to pH3 is 3 to 2. So to convert my moles of H2 into moles of pH3, I will multiply by 2 and divide by 3 as the dimensional analysis tells me to do. So if I use all the H2, I would use 0.331, I would produce 0.331 moles of pH3. Similarly, I began with 0.404 moles of P. The stoichiometric ratio of P to pH3 is 2 to 2. So 0.404 moles of P would produce 0.404 moles of pH3 if it is used entirely. So since the amount of pH3 formed from the H2 is less than the amount of pH3 formed from the P, I know that the H2 must be my limiting reagent. Now find the excess phosphorus that we wasted in the pot. I had 12.5 grams of it to begin with, and that corresponded to 0.404 moles. According to the starting amount of H2, which was 0.496 moles, and the stoichiometry of 2 P's per every 3 H2s consumed, if I use all the limiting reagent, I will only use 0.331 mole of P. I had 0.404 mole of P, so if I subtract what the limiting reagent can use from the total amount of P I started with, I find an excess of 0.073 moles of P, and that this corresponds by multiplying by the molar mass to 2.25 grams of P that I wasted. Now, of course, what that means is that 10.25 grams of P are gone from the initial 12.5 grams of P. Where did it go? Well, it obviously went into the product. So the product contains 10.25 grams of P. It also contains all of the limiting reagent, which was 1 gram of H2. So the total mass of the product I'm forming should be 11.25 grams of pH3, but let's verify that on the next slide. Verify the amount of product formed from the stoichiometry comparing to the limiting reagent. There was 0.496 moles of the limiting reagent that we found from the beginning of the problem. Based on the ratio of pH3 formed to H2 consumed of 2 to 3, that means using all the limiting reagent makes 0.331 moles of pH3, a number we found earlier. Now if I take that number of moles of pH3 times the molar mass of pH3, I find, as I argued on the last slide, that I should make 11.25 grams of the product. And if I check with my masses of reactants used and product formed, they all match up as they should. Now calculating my percent yield, I found on the previous slide a theoretical yield of 11.25 grams of pH3. In the problem statement, it was said that the experiment actually produced 10.2 grams of pH3. So I'll divide the theoretical yield into the experimental yield. I get a fraction of 0.907, and then I multiply that by 100, and get 90.7% yield for this particular experiment.